I'll put on my screen. Hope you can see this. There was this example we had in our last class, which was about a farm that was producing two products, X and Y. And we answered the question using the graphical method, if you remember, on how to determine the number of units to produce for X and Y for the maximum profit. So today I want us to look at the graphical presentation. Just a minute, let me get that particular document. One minute. So Dorcas, hey, are we having a class today? Hello, Dorcas. Mariana.
Yes.
Can you hear me?
Yes.
I just want to confirm if you're able to see on my screen.
Yeah, we can see.
Okay, good. Because this is what I was trying to get from my emails. So I wanted us to look at the simplex method, but just to take you through what we did in our last class, we had already formulated the LP problem or the model itself. We also went ahead and did the calculation of the maximum profit after we had solved the problem graphically at point D, which was actually our optimal point, giving us a profit of around 29 shilling. So today what I want us to look at is the part 2 of this, where this was actually the question asked in that exam, that we find the number of units for product X and Y, which will give us the optimal mix, or rather the optimal solution to the problem, but now using the simplex method. Before we look at this, remember the problem, whether you're doing it under graphical or you're using the simplex method, the problem doesn't change. The way you formulate your LP, it is the same, as long as you remember the points that we talked about. Number one, know what you are doing as your objective, so that you're able to come up with the objective function. Number two, you identify the decision variables. And number three, you come up with the constraints, which are restricting you into achieving your objective. And remember, the last item you should have is the non-negativity condition, although this one is definite, because if it's about a production, let's say, there's no way to which you can produce negative units in the farm. Now, before we solve this using the simplex method, allow me to take you through the steps that we are going to have as we evaluate our solutions of X and the Y units. using the simplex method. So again, I'll still refer to a document that I shared with you earlier on. And again, I took you through this in our last session. And I'll go straight to where we have, you can see what I'm scrolling down, the method we call the simplex method. Step number 1 is to write down the LP problem. And I've said whether you're solving the problem graphically or the simplex method, it doesn't matter. You have the same problem evaluated or rather formulated in the same manner. So the standardization of the LP problem comes into play as your step number 2 when you have already formulated your LP problem. You now go into the standardization of it. And how we do this is by the introduction of what I'll be calling the slacks. And a slack in general is actually an unused resource. Assuming you have already found your maximum value or you already have your optimal point, when you evaluate how much of the resource have been used, you realize that there is maybe a balance. That balance, even in our last class, we said it is the one we call a slack. When we introduce a slack variable in what we call a constraint, and remember the constraints, we said they are written in form of inequalities. In case of a maximization problem, we introduce those slacks. In case we are dealing with a minimization problem, which I'll look in another session, we have what we call the surpluses introduced. So for today, we'll be dealing with slacks because our problem is on maximization. And as I repeat, a slack is an unused resource in a particular case. When those resources are not fully used, the balance is the one we call a slack. So the first thing we do is to assume that there'll be that slack. If the resource will be fully utilized, then the slack value will be equivalent to 0. If not, then there'll be something we can call that particular balance. Now, when we introduce a slack variable in any of the constraints, then our inequalities changes to equations. And I repeat, when we introduce the slack variables in our constraints, all those inequalities, they are going to change to be equations. And then we set up a table where we'll be able now to ask ourselves whether the solution is optimal or it is not optimal. And once we have found the optimal solution finally, we'll be able to say this is a solution to the problem. But as we look at step number 3, we'll have what we call iteration. Iteration is a situation where you keep on asking yourself, have I maximized or have I minimized? In our case, because it's on maximization, we are asking ourselves, have we found the solution that we can call optimal? If not, then we'll go back to some previous stages that we'll have already done until we'll be able to have maximized our value. In other words, we'll have optimized the value after we'll have say, this is what we need to achieve and no further step that will be required. So in our step number 3, as you can see it, there's a lot of workings which you'll go through. Number 1, once we have set up our table, we will identify alongside our value Z, I've used Z because that is what we had in our previous example. We are going to, after we have standardized the objective function, we'll ask ourselves, are there negative values in our law Z? If so, then it means our solution is not yet optimal. And I'll keep on introducing some new terms as we go along, which I've explained in this step, but until, as I said in our last class, until we have an example to go by, one may not be able to understand what exactly do I call a pivot column or even a pivot law. and what are some of the steps that I need to go by up to until the solution is optimized. Okay, so allow me now to take you through this guiding example, the one we had on the May 2018 question. So I've said, because this is a question on maximization, since we had some constraints which were limiting us from achieving maybe the highest possible value, I'll be introducing what we call the slacks. So my assumption is there will be a slack in relation to my first constraint, which is actually the LM1 material. Then I'll also assume there'll be a balance, which I call a slack, in my LM2 material. And so I'll also assume there's another slack variable in relation to my third material constraint, the LM3. So when we are introducing these slack variables, we are going to add them to our first objective function. And once I have added them to my objective function, I'm going to assume their coefficients are going to be 0, because I don't want to change the meaning of my variable of z at the beginning of my workings. So I'll give them 0 coefficients for all the slack variables that I've introduced. Since I had 3 constraints, my slack variables are also 3. S1 for the first constraint, all the way to S3 in relation to the third constraint. And when I am adding them to my objective function Z, I am taking 0 coefficients, meaning they are not changing at all what was my original equation as the objective function. Remember previously, what did we have? Let me take you back. We had the equation, the objective function equation, z is equals to 2x plus y. So if I want the 2x and the y to go to the left-hand side, I will actually take away. But on the right-hand side, I'll be left with a value of 0. I repeat, if I take the 2x plus y to this other side, they'll take negative coefficients. And on the right-hand side, I'm going to be left with 0. So if I come and I add anything on that equation with a 0 coefficient, then it means I'm not changing at all my original equation Z. So what I've done here, I've taken away the 2x and the y. When they are crossing to the left-hand side, they take the negative coefficient, or when a number closes to the other side, it becomes a takeaway. And then when I add the 0s1, 0s2 with these coefficients of 0 zeros, then it means I've not affected my equation. It is still equivalent to my z. Having everything moving to the left, then on the right-hand side, I'll be left with a 0 value. So initially, when we have got no value of our decision variable, x and the y, then the value of our z will be equivalent to 0. Then our constraint number 2 was what? 3x plus 0y less than or equivalent to 27. Since I'd said I assume my slack variable for my first constraint is S1, then if there's any balance here, then I'm not going to have a 0 coefficient for it, because I want that figure to be equivalent to something at the end of the day. If it is 0, it's okay. If it is something else, again, it's okay. But for any other slack variable in relation to the other 2 constraints, for sure they cannot be related to my first constraint, and that's why their coefficients are actually equivalent to zeros. The same I have done to my second constraint, where I've added a slack variable of S2, which is in relation to my second constraint. meaning the first slack variable and the third slack variables, these are going to take 0 coefficients. And so the same happening to my third constraint, where the relation is to the slack variable S3. But again, remember, as much as we saw for the values of X and the Y, those units can never turn to be negative. The non-negativity condition also holds. Now, after we have done our first step, which is actually to standardize our linear programming problem, now you see it is standardized. The standardization of it is coming after we have introduced the slack variables. Class, I now introduce you into how do I want to have these two together. How do I have my working that has been indicated in form of a standardized LP problem into a table? This table, we call it the first table, and I'm going to have it forming what we call a matrix. A matrix relates rows and columns where elements sit in those particular cells or those particular spaces between a row and a column. Now, what I've done in my standardized form to change it into this matrix or to change it into this table, I've just picked the coefficients. And I start with the constraints. I repeat, we start with the constraints. The last one you take is about your objective function Z. So I've written the coefficients of X, Y, the three slack variables that we have introduced. And on my right-hand side, I have just indicated the solutions to the various equations that I have in my working. So how do I go now about getting to understand whether the solution is optimal or not? Once you have set up your first table, you can see on my Z, the coefficients of X, Y, S1, S2, S3 are -2, -1 here, 0, 0, 0, and on the right-hand side, we have the 0 value here. Now, is the solution optimal? The solution of 0, which is my Z value, and remember this was our objective. No. Why? Because on my row Z, I still have the negative variables. The negative variables -2, -1. You'll help yourself by knowing whether the solution is optimal when you'll have had in your row Z all the values becoming positive. If let's say we had a 2, a 1, which are positive on our row Z, we would have said 0 is actually the highest value and so the optimal solution. However, because we still have the negativities on our row Z, then it means our solution is not optimal. Now, the workings begin. When you look at your row Z and there is that highest negative, it's kind of awkward to say this is the highest when we know it's the smallest, but I'm saying the highest negative value of Z, then that helps us to identify what we call the pivot column. The pivot column is the column that corresponds with the highest negative value of a Z that is in case of a maximization problem. When we have the minimization, then we do the reverse. But for now, we are doing maximization problem. So the -2 gives us a column that we can call the pivot column. So the pivot column help us now to take the elements in our identified column to divide the values on the right-hand side so that you'll be able to identify what we call the smallest ratio or ration. what have I done here? After I took my -2, it gave me the pivot column. Then on my right-hand side variables, each of those I divided it by the corresponding elements in my pivot column. I start 27 divided by 3 gives us 9. Then we have 30 here, 30 divided by this 0. And this particular value in mathematics is infinite. And lastly, I have 20 divided by 1 here, which gives us a value of 20. Now, among the variables 9, infinity, and 20, which one do we go for? We want to find the smallest ratio. Usually, we ignore any variable of this kind, a number divided by 0, which becomes infinity. Also, you ignore any variable that is of the kind 0 divided by 0. I repeat, the values that we ignore when we have found our ratios are of the kind infinity, as well as any value that is of the kind 0 divided by 0, because in mathematics, we know that is undeterminable value. So after we have found our 3 ratios here, the smallest is 9, and that 9 to us help us to identify what we call class, the pivot law. Why I took my pivot law to be S1 law is because of the smallest value here, 9. It is the one that helps us to say our pivot law is S1. Now, once we have found our pivot law and our pivot column, what do? Our pivot column becomes our what we call the entering variable. By entering, we mean it will move from a column to now be defined in form of a law. I repeat, by entering, I mean it will have moved from a column to be defined law-wise, so that on the right-hand side, we can have its value. Now, the pivot law will be called the deriving variable, a variable that will give a space to a pivot column variable. So our x here, which is our pivot column variable, will have moved from a column to be defined law-wise, so that at the end of the day, we'll be able to read its value on the right-hand side. And we do away with the entire deriving variable that is S1. So S1 will give way to the X, so that we can be able to have its value at the end of the time. Now, when we have found the pivot law and the pivot column, there's a point of intersection between the column and that law. That point of intersection class is called the pivot element. The point of intersection between the pivot law and the pivot column, we normally call it the pivot element. For example, in this case, our pivot element will be equivalent to 3, which is intersecting the pivot column, which is our column X here, and the pivot law, which is our law S1. Once we have found our pivot element, what do? We are going to take this pivot element, and all the elements in the pivot law are going to be divided by that pivot element. Reason, we want to get the new variables or the new elements, let me call them elements, the new elements for our entering variable x. So that when we are writing down the law x, which is now becoming our new law where the S1 was, it will have taken new elements. And those elements will be given by the elements in S1, okay? Each one of them divided by this particular element we are calling the pivot element. So what we are going to do here, we are going to have our pivot law divided by the pivot element. And I'm going to divide all of them one after the other so that we'll be able to have our variables or the elements which will constitute our new law, which we'll call law S1 divided by 3 equals to our new entering variable, that is law x. So our values of S1 were previously 3, 0, 1, 0, 0. I'm going as per the column elements until we read through the right-hand side variable. So when we divide this one, for example, 3 by 3, we'll have 1. Then 0 by a number is always 0. Then 1 all over 3, 0, 0. And finally, 27 divided by 9. It was coming to a value of what? A value of 3, or rather 9. Sorry, 27 divided by 3 here. We get to divide this one by 3. It will give us a value of 9. And remember, this was actually our guiding element, which we said it's actually our smallest ratio at the end of the day. So once we have found our pivot element, we have taken our pivot law, we have divided each one of those variables by our pivot element, and we have found our entering variable, its elements. Very important, because this is a law that will now give us all the other laws which are going to be written down in our next table. Remember, we set our first table from our standardized form. We have identified our pivot element, our pivot column, our pivot law, but we have also said the pivot column needs to take the place of the pivot law, because pivot column becomes our entering variable, whereas that law becomes our leaving variable. Now, once we have already identified the elements giving us our new entering variable elements, we use that particular law to now come up with all the other laws in our table, which will be formulated as our second table. How do I do this? I will actually consider, let me take you back to the first table, all the elements in my pivot column, apart from the law which I've called now my entering variable, any other element in that particular column has to be changed to a 0. And I repeat, I will use my law that I've called my entering variable to change all the other elements in the pivot column. All this that you can see I'm trying to mark will be changed to zeros. If you already have a 0, like in my S2, I already have a 0, I don't have to interfere with this law at all. After all, the 0 is already established here. But for this one here, yeah, and for this -2, we need to change these 2 to 0 so that we can have the column that is a pivot column apart from where we have our entering variable or the others reading zeros. And what we do, we are going to use our new entering variable, the one we have called x. Those elements that we have found are going to help us now come up with 0 variables here, or 0 elements on our S3 law, as well as the Z law. Let me start with the law S3, because we have said S2 we have already achieved a 0. When we established our first table, we had a 0. We don't want to interfere with that. But for S3, we must change this one to a 0. And again, we change on our law Z, the -2 to a 0. So I'll start with the S3. And how we are going to do that, our old S3 law had the values of our old S3 law was, this is extracted from table 1, okay? 11001 all the way to 20 as our light hand side variable. But how do I make this value here to be equivalent to 0? What I've done, my new law x, which is our entering variable, we had said we take S1, we divide by a pivot element, which was 3, I had a 1 here. So to make a 0 between this 1 and 1, I just subtract. But if I had a 3 here and this was a 1, I would have first of all made this one to be 3. So for my new X law, I've not changed it at all. So because you just look at what is available, which is the simplest way into which you can create a 0. And for me, I saw I had a 1 here. I already have a 1 in my law that I want to convert to a 0. So I just subtract. And don't complicate your work. Just deal with the simplest values as much as possible. And so by subtracting what we have, 0 minus 0, we'll have a 0 here. 1 minus 1, sorry, we'll have a 0. And then 1 minus 0, 1 minus a third, 0, 1. And finally, 20 minus 9, we'll have 11. And remember, whatever you do to the left-hand side, or that you're doing to these elements, you also make sure you do it to the right-hand side, because you want to still retain the same meaning of that particular equation in your table. Lastly, on my law Z, which was, this is from actually our first table, we had a -2. But because I want to use my new X law here with a 1, I question what can I do between this 1 and the -2 to create a 0. And what I did, I took my new law X and I just multiplied by 2, because I had a 1 here to make it a 2, so that when I add -2 and 2, I'll have created a 0. And remember, we have said whatever you're doing to the left, you also do it to the right. Allow me to stop there for a few minutes. We have got less than a minute. We'll be logged out, but come back and log in with the same details, so that at least we can finish up on these workings here. Okay, class.